Good afternoon. Welcome to the ENLACE 2021 Symposium. We're the team number 8. We are Carlos Verdaguer, Carlos Espinosa, Eibar Ortiz, and I'm Elena Payan. And today we're going to share with you our summer research project, which is exploring machine learning methods to classify low temperature stars and brown dwarfs. One of the main tasks of astrophysics is to identify stellar objects. Usually the classification of this object is done visually or by contrasting different astronomical databases, but nothing seems wrong with this. So what is the problem here?
Method for dealing with large data sets, like in this case, astronomical research, because this type of research always takes out really large data sets, and going through each source one by one is extremely hard. So this type of method is really helpful to find how we get UCDs and classify them. Next slide, please. And last but not least, we would like to express our thanks to Dr. Olivia Grave, Professor Adam Bergasser, and our graduate mentors, Roman, Dino, Christian, and Chris. Next slide. And thank you, our audience, for your attention.
Great. Move on. Project 8. Congratulations, Project 7. Project 8, please, yes, good.
Good afternoon. Welcome to the ENLACE 2021 Symposium. We're the team number 8. We are Carlos Verdaguer, Carlos Espinosa, Eibar Ortiz, and I'm Elena Payan. And today we're going to share with you our summer research project, which is exploring machine learning methods to classify low temperature stars and brown dwarfs. One of the main tasks of astrophysics is to identify stellar objects. Usually the classification of this object is done visually or by contrasting different astronomical databases, but nothing seems wrong with this. So what is the problem here? Well, for example, there's a spectrograph at the NASA Infrared Telescope facility with lots of data, about 50,000 objects, making it really, really hard and time-consuming to classify them with the current classifying methods. Now, the principal target is to create a fast, accurate, automated, and easy way to do the classification process. So we propose the use of machine learning tools, allowing machines to learn patterns without specifically being programmed to identify those specific patterns, helping to automate even more the classification process for great amounts of objects. Having mentioned the problem and purpose for this project, what are the main takeaways for everyone listening right now? What we want you to keep are the following ideas. First, we use spectral data and or color of spectral objects to train models to classify between a variety of classes. And the spectral data are measures from specific wavelengths of objects being observed. And second, we use machine learning to automate the process of classifying great amounts of stellar objects.
So now, addressing the problem, the first and most important step before training the model is gathering data and forming a clean and big enough data set with the desired features, which is the information that is going to be used to make predictions. It all starts gathering raw data on several observations at night, normally obtained by a telescope, like the Hubble Space Telescope. The obtained data corresponds to the absorption and emission of light of the astronomical object, which is spectroscopy. Subsequently, that spectroscopy data is reduced and cleaned to moreover be processed and gathered through the SPLAT FIROM package, which stands for SpecSprim Library Analysis Toolkit. And with that package, we managed to build several samples of ultra-cool dwarf, brown dwarf, and non-ultra-cool dwarf spectra. Now, Having our sample of data that include the spectra of several sources themselves, we proceed to train the random forest models with the data having a variety of purposes in a hierarchical organization. First, we classify between ultra-cool dwarfs, which is to distinguish from normal dwarfs from objects like galaxies, supernovas, giant stars, etc. Then we classify the spectral subgroup. Next, we predict the individual spectral type of the source. And finally, classify the M-dwarf stars, which is one of the most abundant. These models are constructed with Fyron and the scikit-learn library, which hosts a wide range of machine learning models. And after we train each random forest, a quantification of the quality of prediction is made to assess the performance of each model.
So now, having trained and built these several random forest models, we now need to assess the quality of these predictions of each model, right? And to do this, there are several classification metrics such as accuracy, precision, recall, and so on. But for practical purposes, we're going to focus on the accuracy metric, which is the most relevant metric. And basically, it's a ratio between the number of correct predictions and the total number of predictions. This metric is observed in the plot seen on screen, and we observe two sets of accuracies for each model, right? One accuracy corresponds to one set of features, and the other one corresponds to another set of features. The first set of features are only the spectral data of each object, and the second one includes in colors or photometry data as a complement to the set of spectral data. We can do this to see if there's any weight that these colors give in for better predictions. And that's why we can also observe these black error bars, marking the uncertainties for these accuracies. And we can conclude two things from this figure: that there's no significant statistical difference in the performance of the model in the addition of colors to the spectral data for training. So we don't actually need these colors, only the spectral data. And as we get to finer classifications, having more and more classes and or less training data, the accuracy decreases. For example, with the first model, we only classify between two classes and actually can deal with a lot of information coming from all objects in the sky survey, while the other models are more specialized and narrowed, dealing with less sources and or more classes. But so far, we've seen which models we used and how good they are. But how to have a better understanding of these models' behave, we can see the following feature importance plots. These figures tell us on which variables or features the model gets the most information to make predictions. In this case, we see these importances represented as bars corresponding to a set of wavelengths, since we're dealing with spectral data. And we see that the finer the classification it is, the random forest models are less selective in the information they gather to make predictions, gathering more information from greater ranges of wavelengths when the problem becomes more complex. And now that we have analyzed our models and assessed their quality of predictions, it's now time to set them on discovery mode and putting them out there to the test by showing them data they haven't seen before and observe what they output on this data. We input 472 new spectra, and what each model outputs can be observed on these three bar graphs, displaying the way each source is classified and how much of each class we get after applying the model. Having them applied on a hierarchical way, meaning that one model is applied on the results of the one before it, the results are somehow as expected. Having mostly ultra-cool dwarfs in the leftmost plot, M and L dwarf subgroups as the most abundant classes in the middle plot, and having the giant and subdwarf classes from the M dwarf types as the less abundant types of stars in the rightmost plot.
Having seen the obtained results, note is a relevant talk about the importance of the development of this work. Through it works and presentation, we have some. That using machine learning mechanisms, it's possible to classify spectral objects without the need for an expert. We can target the future measurements for prediction by focus on the most important fluxes and colors in the edge random forest model. We can obtain a more accurate random forest in the future project. This random forest model can be tested on larger data sets for ever better results, having more balanced classes. These classification models are quite accurate, so they can be used as an AC classification mechanism. By using this method, you could later train using deep learning tools or alternatives, such as TensorFlow or PyTorch. In thus, obtain a really trained model that could be used in a variety of project of purposes. Having said the above, we talk all those who supported of the development of this project. Dr. Oliver Gries, Dr. Adam Burgesser, Christian, Roman, Dino, and Chris for the all support. Continuing, the reference that he used are show. That,
Thank you.
all right, thanks for your attention, Team 8 for the ENLACE program. Wish you an excellent day. Thank you.
And thank you, and sorry for interrupting there, that final slide.
No
Project
problem.
9,
No problem.
congratulations to Project 8.